Hello students, welcome to APG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module Measurement of Power and Wattmeter from the paper Measurements and Instrumentation. From this module, students may get to know about the following topics. First, the power in DC circuits. Second, power in AC circuits. Then, electrodynamometer wattmeters, which have fixed coils and moving coils. Towards the end, we will see the theory of electrodynamometer wattmeters, in which we will study the pressure coil inductance and the correction factor. Students, the power may be defined as the rate at which energy is transformed or made available. The power in a circuit at any instant is equal to the product of the current in the circuit and the voltage across its terminals at that instant. In a DC circuit, if the current and voltage are constant, P is equal to Vi, so that it is necessary only to determine the current and voltage and to take their product in order to obtain the value of the power in the circuit. Alternatively, if the circuit resistance is known, power may be computed from one of the equivalent formula, that is, P is equal to V square by R or P is equal to I square R. In almost all cases, the power in a DC circuit is best measured by separately measuring quantities V and I and by computing power directly with a wattmeter. If voltage and current are measured simultaneously, allowance for power required for operation of voltmeter and ammeter must be made. Of course, the power loss in the ammeter or in the voltmeter is often very small compared to the load power and may be safely neglected. In the case of AC circuits, the instantaneous power varies continuously as the current and voltage go through a cycle of values. The cyclic variation of power has period so short that it can be followed only by special instruments such as oscillographs. However, we are not usually interested in the instantaneous power except where transient phenomena are being studied. So, we are mostly interested in the time average of the power. If the voltage and current are both sinusoidal, the average power over a cycle is given by the expression P is equal to Vi cos phi watts, where V and I are the RMS values of voltage and current, and phi is the phase angle by which current lags behind or leads the voltage. So students, now first of all, let us see the power in DC circuits. The power taken by a load from a DC supply is given by the product of readings of an ammeter and a voltmeter when connected in the circuit as shown in figure 1a. So, the power P is given by V into I watt. It should be taken into account that both ammeter and voltmeter require power for their operation. One can use any of the following two connections as shown in figures 1a and 1b. In figure 1a, the ammeter is connected between load and voltmeter. Therefore, the voltmeter not only indicates the voltage VL across the load, but in addition, voltage drop Vs across the ammeter. If Ra is the resistance of the ammeter, the voltage drop is given by Va is equal to I into Ra, and the power consumed by load is given by multiplication of VL and I, which is equal to V minus Va into I, which in turn gives Vi minus Va multiplied by I. And finally, we get Vi minus I square Ra. Thus, finally, what we get is the power consumed by load is given by power indicated by instruments minus power loss in ammeter. In figure 1b, voltmeter is connected between load and ammeter. Therefore, ammeter not only indicates the current through the load, but in addition, current in the voltmeter also. Current through the voltmeter IV is given by V by RV, where RV is the resistance of voltmeter. The power consumed by load is given by V multiplied by IL, which is given by V multiplied by I minus IV. We can write this as V multiplied by 1 minus V by RV. And the final equation becomes Vi minus V square by RV. Thus, the power consumed by load is given by power indicated by instruments minus power loss in voltmeter. Thus, in both the cases, the power indicated by the instruments is equal to the power consumed by the load plus the power consumed by the instrument nearest to the load terminals. Students, in order to obtain the true power, corrections must be made for power loss in instruments. Under normal conditions, the value of power loss in instruments is quite less as compared with the load power, and therefore the error introduced on this account is very low. However, when the output of the source to be measured is limited, the ammeter and voltmeter may load the circuit too much, thereby causing errors. For a permanently wired installation, when power measurements are required, it would be advantageous to install a wattmeter in place of voltmeter and ammeter. Wattmeter gives direct indication of power and hence multiplying of two readings, as in the case when voltmeter and ammeter is saved. This increases the accuracy of measurements. Now let us see the power in AC circuits. The instantaneous power varies continuously as the current and voltage go through a cycle in the case of alternating currents. However, only the average value over a cycle is more useful, as the average power multiplied by time measures the transfer of energy over a time interval in steady state conditions. The instantaneous power is given by P is equal to Vi, where P, V and I are the instantaneous values of power, voltage and current respectively. Students, thus what we obtain is, if both current and voltage waves are sinusoidal, the current lagging in phase by an angle phi, then V is given by Vm sin omega t, I is given by Im sin omega t minus phi. Therefore, the instantaneous power is given by P is equal to V into I, which is in turn is equal to Vm Im sin omega t multiplied by sin omega t minus phi. Taking theta equal to omega t, we get P is equal to Vm Im sin theta multiplied by sin theta minus phi, which gives us the final equation as Vm Im multiplied by cos phi minus cos 2 theta minus phi divided by 2. Therefore, average power over a cycle is given by P is equal to Vm Im by 2 pi multiplied by integration from 0 to 2 pi of cos phi minus cos 2 theta minus phi whole divided by 2 d theta. Thus, the final expression for the average power over a cycle is given by Vm Im by 2 cos phi. Thus, P is equal to Vi cos phi, where V and I are RMS values of voltage and current, and the cos phi gives the power factor of the load. The presence of cos phi in the above expression for power explains that a wattmeter should be utilized for the measurement of power in AC circuits. This is because of the fact that the use of ammeter and a voltmeter do not take account of the power factor. Students, now let us study about the electrodynamometer wattmeters. It consists of two coils which are connected in different circuits for measurement of power. The fixed coils or field coils are connected in series with the load and so carry the current in the circuit. The fixed coils therefore form the current coil of the wattmeter. The moving coil is connected across the voltage and therefore carries a current proportional to the voltage. A high non-inductive resistance is connected in series with the moving coil to limit the current to a small value. Since the moving coil carries a current proportional to the voltage, it is called the pressure coil or voltage coil of the wattmeter. Now, let us see the construction of the electrodynamometer wattmeters. First, the fixed coils. The fixed coils carry the current of the circuit. They are divided into two halves. The reason for using fixed coils as current coils is that can be made more massive and can be easily constructed to carry considerable current since they present no problem of getting the current in or out. The fixed coils are wound with heavy wire. This wire is stranded or laminated, especially when current is heavy, in order to avoid eddy current losses in conductors. They are first varnished and baked to exclude moisture and clamped into place, thus forming a rigid solid. Second is the moving coil. The moving coil is mounted on a pivoted spindle and is entirely embraced by the fixed current coils. A spring control is used for the movement. The use of moving coil as pressure coil is a natural consequence of design requirements. Since the current of the moving coil is carried by the instrument springs, it is limited to values which can be carried by springs without appreciable heating. A series resistor is used in the voltage circuit and the current limited to a small value, usually between 10 to 50 milliamperes. Next is control. The instrument is controlled by using spring controls, and the damping, the air friction damping is used. The moving system carries a light aluminum vane which moves in a sector-shaped box. Now students, let us see the theory of the working of electrodynamometer wattmeter. The instantaneous torque of an electrodynamometer instrument is given by T is equal to I1 I2 multiplied by dm by d theta, where I1 and I2 are instantaneous values of currents in two coils. Let V and I be the RMS values of voltage and current being measured. Then the instantaneous value of voltage across the pressure coil circuit is given by V is equal to square root of 2 V sine omega t. If the pressure coil circuit has a very high resistance, it can be treated as purely resistive. Therefore, current IP in the pressure coil is in phase with the voltage, and its instantaneous value is given by IP is equal to V by capital R P, which can be written as square root of 2 multiplied by V sine omega t divided by capital R P. Substituting the value for the current, we get the instantaneous value of the current as square root of 2 IP sine omega t. Capital IP is the RMS value of current in pressure coil, and capital RP is the resistance of pressure coil circuit. If the current in the current coil lags the voltage in phase by an angle phi, instantaneous value of current through current coil is IE is equal to square root of 2 I sine omega t minus phi. The instantaneous torque Ti is given as square root of 2 Ip sin omega t multiplied by square root of 2 multiplied by I sin omega t minus phi dm by d theta, which in turn can be written as 2 multiplied by Ip into I sin omega t multiplied by sin omega t minus phi dm by d theta. And the final expression for instantaneous torque Ti is given as Ip into I multiplied by cos phi minus cos 2 omega t minus phi multiplied by dm by d theta. It is clear from above that there is a component of power which varies as twice the frequency of current and voltage. Students, now see the average deflecting torque. Td is given by 1 by t integration 0 to t ti d omega t, which can be written as 1 by t integration 0 to capital T ipi cos phi minus cos 2 omega t minus phi multiplied by dm by d theta d omega t, which is equal to ipi cos phi dm by d theta. Thus, the final term for the average deflecting torque is given by Vi by capital Rp cos phi multiplied by dm by d theta. Controlling torque exerted by springs is given by T is equal to k theta, where k is the spring constant and theta is the final steady deflection. Since the moving system of the instrument cannot follow the rapid variations in torque, the torque has a double frequency component. It will take up a position at which the average deflection torque is equal to the restoring torque of the springs. Thus, at balanced position, k theta is equal to Ip into I cos phi dm by d theta, or the deflection theta is given by Ip by I cos phi dm by d theta whole divided by k. Putting in the values, we get theta is equal to Vi by capital Rp multiplied by cos phi multiplied by dm by d theta, which is equal to k1 dm by d theta multiplied by p, where p is the measured power and is given by Vi cos phi, and k1 is equal to 1 by capital Rp into k. So students, now let us see the wattmeter errors. First, let us see the pressure coil inductance. We have Rp is equal to resistance of pressure coil, capital L is equal to inductance of pressure coil. Resistance in series with pressure coil is represented by capital R. Total resistance of pressure coil circuit, capital Rp, is equal to small rp plus capital R. The voltage applied to pressure coil circuit is represented by capital V, and the current in the current coil circuit is represented by capital I. The current in the pressure coil circuit is given by capital IP, and finally the impedance of pressure coil circuit ZP is written as square root of capital R plus Rp whole square plus omega L square. It was implied in the discussions of the idealized wattmeter that the current in the pressure coil is in phase with the applied voltage. If the pressure coils of the wattmeter have an inductance, the current in it will lag the voltage by an angle beta, given by beta is equal to tan inverse of omega L by capital R plus Rp. It can be seen from figure 4 that for lagging power factor, the angle between current in the current coil circuit and the current in the pressure coil circuit is less than phi, by which the load current lags the applied voltage. The angle between the pressure coil current and the current in the current coil is given by phi prime is equal to phi minus beta. The actual wattmeter reading is given by IPI cos phi prime multiplied by dm by d theta, which can be written as V by ZPK multiplied by I cos phi minus beta multiplied by dm by d theta. Thus, actual wattmeter reading is equal to Vi multiplied by cos phi minus beta divided by K into Rp by cos beta whole multiplied by dm by d theta. In the absence of inductance, Zp is equal to Rp and beta is equal to 0, and therefore the wattmeter will read true power under these conditions. True power is given by V by Rpk multiplied by I cos phi dm by d theta. It is clear from the above expression that in the absence of inductance, the wattmeter read correctly at all powers, factors and frequencies. Taking the ratio of true power and actual wattmeter reading gives us cos phi divided by cos beta into cos phi minus beta. So students, now let us see the correction factor. Correction factor is defined as a factor by which the actual wattmeter reading is multiplied to get the true power. The correction factor for lagging loads is given by cos phi divided by cos beta into cos phi minus beta. It is clear from the phasor diagram that on lagging loads, the wattmeter will read high as the effect of the inductance of the pressure coil circuit is to bring the pressure coil current more nearly into phase with the load current than would be the case if this inductance were 0. Very serious errors may be introduced by pressure coil inductance at low power factors unless special precautions are taken. The wattmeter will read low when the load power factor is leading As in that case, the effect of pressure coil inductance is to increase the phase angle between load current and pressure coil current. Thus, the correction factor for leading power factor is given by cos phi divided by cos beta multiplied by cos phi plus beta. So students, let us summarize what we have learned in this module. We learned about the power in DC circuits. We have discussed in detail the power in AC circuits. We also saw the electrodynamometer wattmeters, which have been explained completely. We have seen the fixed coils, the moving coils, and towards the end we saw the theory of electrodynamometer wattmeters has been derived completely. We have also seen the pressure coil inductance and the correction factor. Thank you.